Welcome back to the Deep Dive. We've got a really interesting piece of research today. It's one of those that I think, frankly, anyone working in model architecture really needs to have on their radar.
Oh, absolutely. This one's a big deal. We're looking at understanding the skill gap in recurrent language models coming out of Carnegie Mellon, MBZU AI, and Cartesia.ai.
And it really gets to the heart of this central tension in our field, right?
It does. It's the big trade-off. You've got the quadratic scaling of transformers on one side.
Like your llamas and your GPTs.
Yeah.
Powerful, but so expensive as context gets longer.
Exactly. And on the other side, you have the state space models, the SSMs like Mamba. They're incredibly efficient, linear scaling.
The holy grail for long context.
But they've always had this performance ceiling. There's a persistent skill gap, especially on certain kinds of tasks.
Right, and we usually talk about that in very abstract terms, like compression loss or something.
Yeah.
But what's so great about this paper is they don't settle for that kind of hand-waving.
No, they nail it down. They identify a very specific mechanism that they call Gather-and-Aggregate.
And they argue it's how both architectures try to solve retrieval tasks.
And the punchline is that the gap isn't a failure of the whole SSM idea. It's a very specific breakdown in one part of that algorithm.
Which means it's potentially fixable. But, okay, before we get to the fix, we have to talk about the diagnosis. And that starts with MMLU.
Yeah, this was a huge aha moment for me in the paper. We all think of the MMLU benchmark as a test of knowledge.
Of course, it covers everything from anatomy to philosophy. High score means a smart, knowledgeable model.
That's the assumption. But the authors argue that if you look at the structure, it's actually a retrieval task.
A retrieval task?
Think about it. You get a question, then options A, B, C, and D. To get it right, the model has to map its internal knowledge to one of those specific labels from the context. It's a pointer problem.
You have to find the token for B that corresponds to the right answer.
Precisely. And they proved this with a really, just a brilliant ablation study on Llama 3.18b.
The model lobotomy.
Basically, yeah. They started removing layers from the end of the model one by one to see what would break.
And for most knowledge-based tasks, like Winogrand, the performance just degraded smoothly.
As you'd expect. You remove some compute, the model gets a little bit worse. It's a nice, clean, linear decline.
But not for MMLU.
Not at all. For MMLU, the performance stayed completely flat. The model was just as good with 30 layers as it was with 32. It was really strange.
Until they hit the critical layer?
Exactly. The moment they removed layer 17 from Llama 3.1, the MMLU score fell off a cliff.
And we're not talking a small dip.
No, it went from about 66% accuracy straight down to 25%. Random guessing.
Wow. So that capability isn't distributed across the network at all. It's localized.
Highly localized. They found the entire skill really relies on just two layers, 16 and 17 in this case.
And they went even deeper, right? Down to the head level.
They did. And this is where it gets even more extreme. In that Llama model, disabling just one single head L17H24, head 24 in layer 17 caused the same exact crash.
The entire benchmark performance hinges on one head.
One head out of hundreds. And they saw something similar in a pure SSM model, Falcon Mamba. There, it was just 4 channels driving the whole thing.
So this is a tiny, specialized circuit.
A very specialized circuit running a specific algorithm, and that algorithm is what they call Gather-and-Aggregate.
Okay, let's unpack that. It's a 2-stage process. Stage 1 is gather.
Right. And you can think of this as compression. The model needs to take a chunk of text, like option A, the sky is blue, and basically squish all that meaning down to a single location.
And the paper's visualizations here are amazing. You see the attention maps just lighting up on the delimiter tokens.
Specifically the new line character, N. That comes right after the text of the option.
So that new line token becomes a little summary, a stand-in for the whole phrase.
Exactly. That's the gather head at work. It attends to all the words in the option and pours the meaning into the vector for that new line token.
Okay, so that's gather. Then comes stage 2, aggregate.
And this happens in that critical layer 17. The aggregate head is the decision maker.
And it's not looking at the original text anymore, is it?
No, that's the key. It almost exclusively looks at those summary tokens, the new lines. It's like it's just browsing a menu of the compressed option.
Okay, it picked one.
It performs what's essentially an argmax operation. It finds the summary token that best matches the question and then moves that information to the end to generate the final answer, A or B or whatever.
So gather compresses, aggregate selects. A simple powerful algorithm.
And both Transformers and SSMs are trying to run it. The problem is SSMs are not very good at the second part.
Right, and this gets to the core of the skill gap. Why? If it's the same algorithm, what's the problem?
It comes down to a fundamental difference. A Transformer's attention is discrete. It can be incredibly sharp, like a digital switch. It can decide to put 100% of its attention on one token and 0 on everything else.
It's precise.
Very. An SSM, on the other hand, is updating a continuous hidden state. It's more like a smooth wave or a dynamic system.
So it can't make those sharp distinctions.
And that causes what the paper calls leakage. When the SSM tries to gather the info for option A into its summary token, some information from the surrounding text, it just leaks in. The boundaries are fuzzy.
So the summary for option A is contaminated with a little bit of option B.
You got it. And that makes the aggregate step a nightmare. The aggregate head tries to pick the best summary, but all the signals are blurred together. It can't make a clean choice.
Which explains another one of their findings, the redundancy.
Exactly. That's the SSM trying to compensate. Llama got to 98% of its score with just one aggregate head. Falcon Mamba needed 4 different channels just to get to 86%.
It's using more components to try and average out the noise.
It's brute forcing the precision that it naturally lacks, and it just can't match the sharpness of a true attention head because that argmax operation, that pick one function, is what attention is natively built for.
Okay, so we have the diagnosis. The SSM is leaky, and it struggles with the sharp selection required for the aggregate step.
That's the hypothesis. And this is where the paper gets really practical, because they test this idea using hybrid architectures.
Right, let's talk about the solutions. They looked at Zamba 2, which is one of these models that mixes Mamba layers and attention blocks.
And they did a similar ablation study. They found the specific attention heads that were doing the aggregation job, and when they knocked out just 9 of those heads,
Leaving all the Mamba layers untouched.
completely intact, the MMLU score dropped by a factor of 4.
Which proves the Mamba layers were just offloading that one critical task.
It's a clear division of labor. The Mamba parts do the efficient, continuous processing, but when it's time for a sharp, discrete choice, the model hands it off to the attention heads. They're the specialists.
My favorite experiment, though, was the Lamba model, the Frankenstein model.
The replacement experiment. Yeah, this was just brilliant. They took a distilled Mamba model that was terrible at MMLU scoring around 33%.
Basically just above random chance.
Right. And they started swapping in individual layers from its teacher, the original Llama 3 model. They swapped in an early layer, like layer 5. Nothing happened.
Score stayed flat.
Swapped in a middle layer, layer 10. Again, nothing. But then
They swapped layer 17.
the critical layer, they replaced just the Mamba layer 17 with the Transformer layer 17, the one with the real aggregate head. The MMLU score jumped from 33% to 50%.
Just from that one layer.
One single layer. It's the most definitive proof you could ask for. The bottleneck is the aggregation mechanism, and it's located at a specific depth in the network.
This all leads to a very clear design recipe for anyone building these models, doesn't it?
It really does. It gives us a theoretical grounding for where to place attention layers in a hybrid model.
You don't need them everywhere.
No, that defeats the purpose. You want them in the middle to late layers, right, where this gather and aggregate mechanism tends to emerge naturally. Let the SSMs handle the efficient early stage processing.
And then bring in the attention for the decision making.
Exactly. And for model distillation, the advice is even more pointed. The paper basically says, don't even try to teach an SSM to do this sharp aggregation.
You can't distill it.
You can't. You'll lose all the fidelity. They recommend you identify the key aggregate heads in your big teacher model and just copy-paste them directly into your smaller student model.
Keep those few components as true attention heads.
Yes. Don't force the model to do something it's structurally bad at. Give it the right tool for the job.
It's such a shift in thinking.
Yeah.
Away from this transformer killer mindset and towards a more surgical, best of both worlds approach.
It's efficiency through specialization. We're learning which parts of the architecture correspond to which, well, cognitive primitives.
So before we wrap up, I want to go back to MMLU for a second. This whole paper kind of changes how I see those leaderboards.
It demystifies them quite a bit, yeah.
It really does. You see a model with a huge MMLU score, and you assume this deep general reasoning. But this work shows you can completely destroy that score by deleting a single head that's just good at copy-pasting a letter from the context.
It raises a pretty profound question about the benchmark. Are we measuring intelligence, or are we measuring the precision of one specific matrix multiplication at layer 17?
If what we call reasoning on these tests is just a very, very precise retrieval function, then the line between memory and intelligence gets incredibly blurry.
Or maybe what we call reasoning is just a sophisticated cascade of these simpler mechanisms like gather and aggregate. Maybe we're the ones over-interpreting it.
That's a humbling thought, that the difference between genius-level performance and random guessing can come down to one well-placed pointer.
It definitely forces us to be more rigorous. But on the bright side, for a builder, it's great news. The skill gap isn't some unknowable mystery anymore.
No, it's an engineering problem.
It's an engineering problem with a clear, targeted solution.
A solvable problem. Well, we'll leave it there. A huge thank you for joining us on this deep dive. As always, you can find a link to the paper itself in the show notes.
Thanks for having me.